Tonight, we are going to sit with a silence that should not exist. Not the silence of an empty room, not the silence of a quiet night, not the comfortable silence of a world that is simply asleep. The silence of an entire universe that by every serious calculation astronomers and physicists have ever run should be full of voices, and is not. This is the Fermi paradox. The name makes it sound like a technical problem in astrophysics, something that experts debate in journals and then file away. It is not. It is one of the most unsettling questions that has ever been asked seriously, and its most consistent answers are the most unsettling things about it. The reason it is called a paradox is not because the math is complicated. The math is almost embarrassingly simple. The reason it is called a paradox is because the two sides of the equation point in opposite directions and cannot both be true. Side 1. The universe is ancient, vast, and filled with the conditions for life. Our galaxy alone contains somewhere between 100 and 400 billion stars. The Kepler Space Telescope has shown us that most of those stars have planets, and that billions of those planets are rocky worlds in regions where the temperature allows liquid water to exist on the surface, given the right atmospheric conditions. The chemistry of life, carbon and hydrogen and oxygen and nitrogen and phosphorus, these elements are not special. They are among the most common in the universe. They appear in interstellar gas clouds, in meteorites, in the atmospheres of distant planets, in the tails of comets. Everywhere that chemistry can happen, the building blocks of biology are present. And the universe has had 13 billion years for this chemistry to run. By any reasonable estimate, using the parameters we now know from decades of exoplanet observation, stellar surveys, and astrobiology research, the universe should be teeming with life. A fraction of that life should have evolved intelligence through the same kinds of selective pressures that produced intelligence on Earth. A fraction of that intelligence should have developed technology. A fraction of that technology should be producing signals and structures and modifications to the physical environment that cross interstellar space and arrive here in some form we can detect. The estimate does not require most of these fractions to be large. Even if almost everything fails at almost every step, the numbers are large enough that something should be detectable. Side 2. Silence. Complete, total, and increasingly inexplicable silence. We have been listening for 6 decades. We have searched billions of radio frequencies. We have surveyed the infrared signatures of millions of stars looking for megastructures. We have found nothing that requires an intelligent explanation. The longer we look, and the more sensitive our instruments become, the more thorough the silence appears, not more certain, because our coverage remains limited. But the constraints do tighten as the search expands. The space of possible explanations that fit the data grows smaller with each decade of negative results. By the end of tonight, you will understand every major explanation that serious researchers have proposed for why the universe is silent, which explanations the evidence supports, which ones cause unease even among the scientists who propose them, and what the silence might actually mean for a civilization that is, right now, at the exact stage where the silence predicts things go wrong. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now let's begin. Enrico Fermi was a physicist who worked on the Manhattan Project. He was among the most brilliant scientists of the 20th century, a man who could calculate and estimate in his head with a precision that astonished colleagues trained in the same discipline. In 1950, he was working at Los Alamos National Laboratory in New Mexico, when he and a few colleagues walked to lunch together, and the conversation turned, as conversations in 1950 sometimes did, to a cartoon in the New Yorker about flying saucers stealing New York City trash cans. They talked about it for a few minutes, debating the plausibility of alien visitors. The conversation moved on. They reached the dining hall. They sat down. They talked about other things. And then, a few minutes later, Fermi looked up from his food and asked, apparently with no connection to what they had been discussing, "Where is everybody?" His colleagues knew immediately what he meant. The question was not about the cartoon or about that specific lunch. It was about the numbers, the deep and simple calculation that Fermi had evidently been running in the back of his mind while the conversation moved on, a calculation that had arrived at a result he could not reconcile with the world he could observe. If intelligent life is common in the galaxy, where are the signals? Where are the ships? Where are the megastructures, the modifications to star systems, the artifacts in our solar system, the radio transmissions that should be crossing space in all directions from a galaxy that has been making stars for 10 billion years? Where is any evidence at all that anyone else has ever existed out there? The question sounds simple. It sounds like the kind of thing a curious child might ask. But the deeper you go into the math, the more disturbing the silence becomes. Because the math says the silence should not exist. The galaxy is roughly 100,000 light-years across and about 13 billion years old. It contains somewhere between 100 and 400 billion stars, most of which are not much different from our Sun in the ways that matter for planet formation and habitability. The Kepler Space Telescope, which stared at a single patch of sky and measured the brightness of over 150,000 stars, found that most of those stars have planets, and that a significant fraction of Sun-like stars have rocky planets in zones where liquid water could exist. Extrapolated to the galaxy, this means there are likely billions of potentially habitable worlds in the Milky Way alone. The chemistry of life, carbon, hydrogen, oxygen, nitrogen, sulfur, phosphorus, these elements are not rare anywhere. They are produced in stellar cores and distributed through supernova explosions. They are in the interstellar medium. They are in meteorites. They are in comets. They are in the atmospheres of gas giants and on the surfaces of moons. Anywhere that chemistry can happen, the building blocks of biology are available. Life on Earth appeared remarkably quickly after the planet formed. Earth is about 4.5 billion years old. The earliest evidence for life, microfossils and chemical signatures in ancient rock, dates to roughly 3.7 billion years ago. Some evidence suggests even earlier origins. The planet was barely cool, the bombardment from the late heavy bombardment period barely subsiding, before something started self-replicating in the warm chemical soup. If life is that eager to begin on Earth, if it appears within a few 100 million years of the conditions becoming favourable, why would Earth be exceptional? And here is the calculation that Fermi was running at that lunch table. Even if only a tiny fraction of the stars in the galaxy have planets where life starts and eventually produces intelligence, and even if only a tiny fraction of those intelligent species ever develop the technology to cross the space between stars, and even if they only travel at a very small fraction of the speed of light, the math shows that a single civilization with a head start of even a few million years could have spread throughout the entire Milky Way galaxy by now. A few million years sounds like a long time in human terms. In a 13 billion year old galaxy, it is nothing. It is 0.2% of galactic history. It is a rounding error. If even one civilization in the galaxy had emerged a few million years before us and decided to expand, they would be everywhere by now. Every star. Every planet. Every corner of the galaxy within reach of travel at even a small fraction of the speed of light. The evidence of their existence would be impossible to miss. We would know about it in the way we know about the existence of the sun, not because we searched for it, but because it is undeniable. We do not know about it. We have been looking. We have built radio telescopes and pointed them at the sky. We have searched billions of radio frequencies for narrowband signals of the kind that natural processes do not produce. We have looked for infrared excesses in surveys of millions of stars, anomalous signatures that would indicate a civilization harvesting stellar energy. We have looked for unusual dimming patterns in stellar light curves that might indicate megastructures in orbit. We have examined the geological and archaeological record of Earth for signs of ancient visitors. We have listened. We are still listening, across more frequencies and with greater sensitivity than ever before. The sky is silent in every way we currently know how to look, and every time we improve our instruments and expand the scope of the search, the silence becomes more thoroughly confirmed rather than less. That is the paradox. The universe should be full. The universe appears empty. Both of these statements are grounded in real evidence, and they cannot both be true. So one of them must be wrong, or our understanding of one of them must be incomplete. And whatever the explanation turns out to be, it will be one of the most important things humanity has ever learned about the universe and about itself. The first thing people usually reach for when they confront the Fermi paradox is simple. They are just too far away. Space is enormous. Even at the speed of light, signals take years to cross the distances between stars, and civilizations are probably spread thin enough that we just have not heard anyone yet. This sounds reasonable. It sounds like the sensible, moderate, non-alarming answer. It is wrong, or at least deeply insufficient. The reason it is insufficient is the age problem. The galaxy has been making sun-like stars for billions of years. If life tends to emerge on planets around those stars, then civilizations should have been emerging for a very long time. A civilization that emerged just 1 billion years ago would have had 1 billion years to develop technology. 1 billion years is roughly 200 times the entire history of modern humans. It is roughly twice the time since the earliest multicellular life on Earth. What can you do with 1 billion years of technological development? We have no idea. We genuinely have no idea what the upper ceiling of technological development looks like. In the last 200 years, humans went from horse-drawn carriages to landing robots on Mars and detecting gravitational waves from colliding black holes. In the last 50 years, we went from pocket calculators to devices in your pocket that can access nearly all of human knowledge instantly. Project that forward by 1 billion years, and the answer is not more of the same. The answer is something we do not have concepts for. 1 billion-year-old civilization would not be driving faster cars. They would be operating at scales and in ways that would be invisible or incomprehensible to us. Or they would be visible from light years away, or they would be impossible to miss. So the distance argument does not actually solve the paradox. It just delays the question. If civilizations can emerge and develop, they should have left some trace. Some signal. Some structure, some pattern in the noise of the universe that says, "We were here. We have found nothing." In 1977, an astronomer named Jerry Amon was doing routine volunteer work reviewing strips of computer printout from the Big Ear Radio Telescope at Ohio State University. The telescope had been systematically scanning the sky as part of an ongoing SETI survey, recording signals at multiple frequencies simultaneously. Eamon had been going through the data for some time when he noticed a cluster of numbers and letters in one column that was dramatically different from the surrounding noise. He circled it with red pen and wrote a single word in the margin. Wow, the signal had emerged from the noise like nothing he had seen before in years of reviewing this data. The signal had lasted 72 seconds, the amount of time the Earth's rotation would carry a fixed point in the sky through the telescope's beam. It was a narrowband signal at 1,420.4556 MHz, precisely the emission frequency of neutral hydrogen, which had been theorized since the 1950s as the most likely frequency for any deliberate interstellar transmission. The logic was universal. Hydrogen is the most abundant element in the universe. Its spectral emission frequency is a fundamental constant of physics, and any civilization that had done basic astronomy would know it. If you wanted to broadcast to civilizations you had never met, you would broadcast at a frequency they could identify from first principles. The signal was roughly 30 times stronger than the background noise level in that frequency band. It had the precise shape expected from a signal originating at a fixed point in the sky, rather than from a source following the telescope's motion. It showed none of the frequency broadening that would be expected from an object within the solar system. Everything about it matched the profile of a signal coming from a point source at interstellar distance. It was never detected again. The silence that followed was as total as the original signal was anomalous. Dozens of follow-up observations at the same sky coordinates in the following weeks, and hundreds more over the following decades at higher sensitivity produced nothing comparable. Hundreds more observations over the following years and decades, including by other telescopes with greater sensitivity, produced nothing. In 2020, astronomers proposed that the signal might have been produced by hydrogen gas associated with a comet, but this explanation has been disputed and is not universally accepted. The WOW signal remains the most compelling candidate for an extraterrestrial radio signal ever recorded. It remains completely unexplained after nearly half a century. It could have been a natural source, some astrophysical process producing a narrowband signal at exactly the hydrogen frequency that we have not identified. It could have been interference from a human-made satellite or aircraft that happened to align with the observations. It could also have been exactly what it appeared to be. The reason the WOW signal matters in the context of the Fermi paradox is not because it proves anything. It is because it shows what we are looking for, and it shows how close we might have come to finding something and then lost it. The universe is enormous. Our searches cover tiny fractions of the sky for tiny windows of time. If a civilization is broadcasting intermittently, or in only one direction, or only at certain times, or at frequencies adjacent to the ones we monitor most closely, we could miss signal after signal even if they were happening continuously. The silence might be partly a product of our limited attention, but only partly. Because we have also run systematic, sustained, wide-band searches. SETI programs have been operating for over 60 years. The Breakthrough Listen initiative, launched in 2015, has been conducting one of the most sensitive and comprehensive radio searches in history, covering billions of frequency channels across large fractions of the sky. Surveys have been thorough enough that a signal powerful enough to be comparable to what we produce from Earth could have been detected from anywhere within several hundred light years. Nothing that could not be explained has been found. The physicist Nikolai Kardashev proposed in 1964 a scale for measuring civilizational advancement in terms of energy consumption. It is useful for the Fermi paradox not because it answers the question, but because it clarifies what we should expect to be visible if advanced civilizations exist. A Type 1 civilization, by Kardashev's definition, uses all the energy available on its home planet. A Type 2 civilization uses all the energy output of its host star. A Type 3 civilization uses all the energy of its host galaxy. Where does humanity fall on this scale? We currently use approximately 10 to the 13 watts of power, which is about 0.0001% of what a Type 1 civilization would use. We are not Type 1. We are perhaps Type 0.7 on a logarithmic interpolation. We are partway up the first rung of a ladder that extends to almost inconceivable heights. The relevance to the Fermi paradox is straightforward. A Type 2 civilization, harvesting the energy of its host star through a Dyson sphere or similar structure, would be detectable from thousands of light years away. The infrared signature of the waste heat from such a structure would stand out against the natural infrared background of the galaxy. We have searched for these signatures, as described with the WISE survey, and found nothing convincing. A Type 3 civilization would be detectable from intergalactic distances. It would be visible in galaxy surveys. A galaxy in which a Type 3 civilization had established itself would look different from other galaxies. We have surveyed millions of galaxies. None of them show unambiguous signs of Type 3 occupation. The absence of Type 2 and Type 3 signatures in our astronomical surveys is one of the strongest pieces of evidence for the Fermi paradox. These are not subtle signals. They are not narrow-band radio transmissions that could be missed by pointing in the wrong direction for a few seconds. They are macroscopic modifications to astronomical objects that would be detectable with existing telescopes from enormous distances. If Type 2 and Type 3 civilizations are absent, one of two things is true. Either no civilization has ever reached Type 2 or higher, which would mean intelligence is rare or short-lived, or Type 2 and 3 civilizations exist, but are somehow invisible, which would require that they build in ways that do not produce the infrared and other signatures we would expect. The second option is not impossible. Perhaps advanced civilizations find ways to make their energy use extraordinarily efficient, approaching thermodynamic limits that make them nearly invisible. Perhaps they have access to energy sources we do not understand. Perhaps they dismantle megastructures after a period of use, and the current epoch happens to have none active. But the first option, that no civilization has reached Type 2 in the entire observable universe, has a straightforward implication. The path from Type 0.7, which is where we are, to Type 2 is either never completed by any civilization, or is completed only rarely enough that none are currently active within the volume of the universe we can survey. The Kardashev scale provides a framework for being precise about what kind of absence we are observing. We are not just observing the absence of radio signals, we are observing the absence of stellar engineering, and that is a considerably more significant absence. Radio signals could be missed for many reasons: wrong frequency, wrong direction, wrong timing, communication methods we have not thought of. The absence of stellar-scale engineering is harder to explain away, because stellar-scale engineering produces signatures detectable across the galaxy regardless of the specific technology involved. An infrared excess from waste heat is not a technological signature in the narrow sense. It is a thermodynamic consequence of any energy-intensive process. You cannot hide it. The fact that no star in our observational neighborhood shows a convincing Dyson sphere signature suggests one of three things. either no civilization has ever reached the energy level that would motivate stellar-scale engineering, which means intelligence is rare or short-lived before it can reach that level, or civilizations reach that energy level but universally choose not to build in ways that produce thermodynamic signatures, which requires explaining why every civilization in galactic history made the same unusual choice. Or they build with near-perfect efficiency that approaches physical thermodynamic limits. None of these is a comfortable answer. None of these explanations is comfortable. They all converge on the same implication. Something about the trajectory from technology-capable intelligence to galaxy-spanning civilization is blocked. Not just slowed. Not just made improbable. Blocked. Consistently across the full range of civilizations that have ever attempted the path. There is a calculation that sits at the center of every serious discussion of the Fermi paradox. It is called the Drake equation, after the radio astronomer Frank Drake, who wrote it on a blackboard in 1961. The Drake equation is not a scientific formula in the usual sense. It cannot be solved to give a precise answer because most of its variables are unknown, but it is useful because it forces you to be explicit about what you do and do not know. It breaks the problem of estimating the number of detectable civilizations in the galaxy into a series of smaller questions, each of which can be examined separately. The equation asks, how many stars form in the galaxy per year, multiplied by the fraction of those stars that have planets, multiplied by the average number of planets per star system that could support life, multiplied by the fraction of those planets where life actually emerges, multiplied by the fraction where intelligence evolves, multiplied by the fraction where technology develops, multiplied by the average length of time such a civilization remains detectable. When Drake first wrote the equation on a blackboard at the National Radio Astronomy Observatory in Greenbank, West Virginia, in November 1961, almost all of the variables were pure guesses. At that time, no planet had been confirmed around any star other than the Sun. The frequency of planets around other stars was unknown. The biology and evolution factors were entirely speculative with no empirical foundation. The equation was less a numerical calculation than a structured argument, a way of forcing the problem into a form where each unknown could be named, bounded, and eventually measured. Since then, several of the early factors have been dramatically constrained by observation. We know stars form in this galaxy at a rate of roughly 1 to several per year. We know from the Kepler mission that planets are extremely common, with most Sun-like stars hosting planet systems and a significant fraction of those having rocky planets in or near the habitable zone. By some estimates, there are billions of potentially habitable rocky planets in the Milky Way alone. The astronomical factors push the expected count of civilizations upward. The unknowns are the biological and social factors. How often does life start once the conditions exist? This we cannot know from one example. How often does life become intelligent? Again, one data point. Life on Earth was microbial for roughly 3 billion years before multicellular organisms appeared, and intelligence in the human sense is a recent and apparently rare development even among Earth's millions of species. How often does an intelligent species develop technology? And how long does a technological civilization last before it destroys itself, collapses, or stops producing detectable signals? That last variable is where many researchers now think the resolution to the Fermi paradox hides. And the reason it matters is that we may be currently determining our own species' value of it. The most optimistic resolution to the Fermi paradox is called the rare Earth hypothesis, developed most fully in the 2000 book of the same name by paleontologist Peter Ward and astronomer Joe Kirschvink. It says the paradox is not really a paradox. The expected number of civilizations in the galaxy is simply very small, because the conditions required to produce complex intelligent life are much more specific and much less common than the simple habitability calculation suggests. Earth is not just a planet with liquid water. It is an improbable convergence of conditions, each of which may be uncommon individually, and whose combination may be extraordinarily rare. A star that is stable over billions of years without extreme UV flares or dramatic luminosity changes. An orbit that remains in the habitable zone for long enough that evolution can work to its full potential. A large moon, probably the result of a specific collision event in Earth's early history, that stabilizes the axial tilt and prevents the wild climate swings that would result from a planet whose polar orientation drifts chaotically. Plate tectonics, which recycles carbon dioxide from the atmosphere into the mantle and back, acting as a thermostat that keeps temperatures within a range compatible with complex life over geological time. A Jupiter-sized planet in the outer solar system that deflects many potentially lethal comets and asteroids that would otherwise reach the inner planets at high frequency. A location in the galactic habitable zone, far enough from the violent central bulge that gamma-ray bursts and stellar density do not create a sterilizing environment, but not so far out that the heavy elements needed for rocky planets and complex biochemistry are scarce. Each of these factors might be common individually. The argument is that, together, they are rare. The rare Earth hypothesis says intelligent life requires not just a habitable planet, but a specifically habitable planet with a very long list of properties that happen to co-occur, and that such specific combinations are uncommon enough that the galaxy is mostly empty of intelligent life, even if it contains many planets with simple microbial organisms. If the rare Earth hypothesis is correct, the silence makes sense without any need for catastrophe. We are alone, or nearly so. The universe is not failing to answer. It has very few answers to give. The rare Earth hypothesis is reassuring in a specific way. It says the silence is a statistical consequence of rarity, not a warning about the future. It says we are special in the literal sense, genuinely unusual, perhaps nearly unique in this galaxy, products of an improbable convergence of conditions that elsewhere has not converged. The silence is simply the sound of a mostly empty room, and we are unusual furniture. The hypothesis also has some observational support, though each piece of evidence is contested. The galactic habitable zone argument, that complex life can only emerge in regions of the galaxy that are neither too close to the violent central bulge, where supernova rates are high and radiation intense, nor too far from the metal-enriched inner disk, where heavy elements for rocky planets are abundant, does geometrically constrain the number of suitable stars to a ring-shaped region rather than the full galaxy. The specific role of a large moon in stabilizing Earth's axial tilt may be more important than typically acknowledged, and large moons of this type may be rare outcomes of planetary formation. The absence of any detected extraterrestrial microbial life in our solar system, if confirmed, would be one of the strongest pieces of support for the rare Earth hypothesis available. The problem is that the hypothesis requires many independent factors to each be improbable, and in the same direction. Any individual factor can be argued to be rare, but the more factors you stack without independent confirmation of each being rare, the more the hypothesis begins to feel like a motivated construction rather than a discovered pattern. And a deeper mathematical problem remains regardless. Even if intelligence is very rare, even if only 1 in a billion star systems produces an intelligent species, There are roughly 100 to 400 billion star systems in this galaxy. 1 in a billion still gives you anywhere from 100 to 400 intelligent civilizations. The rare Earth hypothesis reduces the expectation, but it does not bring it to zero. And if even one of those civilizations emerged 1 billion years ago with any interest in exploring the galaxy, by the Hart-Tipler argument, we would see evidence of it. The rare Earth hypothesis does not prevent a single ancient exception. But we see no exception at all. The rare Earth hypothesis reduces the expected number of civilizations. It does not eliminate the paradox. For the hypothesis to fully explain the silence, intelligence must be so rare that the galaxy contains only us, or nearly only us, while also producing no ancient civilizations in all of galactic history that had billions of years to expand before we arrived. Even one exception in 13 billion years would have had time to be everywhere. The rare Earth hypothesis requires not just rarity, but near total rarity across all of time. That is an extraordinarily specific degree of rarity to justify on the basis of the factors proposed. It is possible, it may be true, but it requires a coincidence of conditions so precise that many researchers find it less parsimonious than alternative explanations. A more uncomfortable resolution is called the Great Filter. The Great Filter is the idea that somewhere along the path from simple chemistry to galaxy-spanning civilization, there is a step that is extraordinarily difficult to pass. So difficult that almost no species ever makes it. A filter so fine that the vast majority of evolutionary lineages that reach it are terminated by it, not by extinction in the ordinary sense, but by some fundamental barrier that prevents the transition to the next stage. Not a killer, exactly, a ceiling. The place where the climb stops. The concept was first articulated in a 1998 paper by economist Robin Hanson titled "The Great Filter, Are We Almost Past It?" The question in the title is the entire structure of the argument. Either the filter is behind us, meaning we have already passed through it, or the filter is ahead of us, meaning we have not. If the filter is behind us, the universe is the way it is, because the step we already survived was the rare one. The candidates for this filter are numerous. Life starting from chemistry at all, the emergence of the first self-replicating molecule from non-living chemical systems, may be extraordinarily improbable. The transition from simple bacteria like cells, prokaryotes, to the more complex cells with nuclei and internal organelles, called eukaryotes, is another candidate. This transition happened exactly once in Earth's history, roughly 1.5 to 2 billion years ago, despite billions of years of opportunity. The emergence of multicellular life is another. Sexual reproduction. The development of nervous systems complex enough to produce behavior. The emergence of language and cumulative cultural transmission. The ability to pass learned knowledge across generations. Any of these could be the great filter, the thing that almost never happens, and we got lucky. If the filter is behind us, the universe is mostly empty, not because civilizations always end, but because civilizations almost never begin. Our existence is the exception. We are the lottery winner. We survived the difficult part. The future, while never guaranteed, is open. This interpretation is genuinely reassuring. It says the silence is a statistical consequence of rarity, not a warning about what comes next. It says that the hard step was in our past, not in our future. But if the filter is ahead of us, the implications are very different and much darker. If the filter is ahead of us, it means that the early steps, life starting, cells complexifying, intelligence emerging, are not the bottleneck. civilizations form. They develop technology. They reach something like our current stage. And then something stops them. Something happens that terminates technological civilizations before they can make their presence known across the galaxy. And it happens consistently, reliably, almost without exception, because if it did not happen consistently, we would see the survivors. What could consistently terminate technological civilizations? The obvious candidates are the ones that grow directly from the technologies that define a civilization as technological. Nuclear weapons capable of civilizational scale destruction. Engineered pathogens, biological organisms modified to be more lethal or more transmissible than anything evolution has produced. Climate change severe enough to destroy the agricultural and industrial base that complex civilization depends on. Artificial intelligence systems that pursue objectives misaligned with the survival and flourishing of the civilization that created them. These are not imaginary threats. They are not science fiction scenarios projected into a distant future. They are present in human civilization today at various stages of development. Nuclear weapons have existed for less than 80 years and have been brought close to use on multiple occasions. Biological engineering capable of creating novel pathogens is advancing rapidly. Climate change from industrial activity is measurably underway. Artificial intelligence is developing at a pace that outstrips the regulatory and governance frameworks humans have built. If these threats tend to emerge before a civilization develops the capability to spread beyond its home planet, the filter works as follows. Civilizations develop exactly the things that make them capable of interstellar communication, and those same things, combined with the social and political structures of species that evolved under very different pressures, tend to terminate civilizations before they can use what they have built to survive. The silence of the universe in this reading is not the silence of an empty room. It is the silence after a series of events that no one survived to report. The pattern is not visible to us because we are inside it. We can only see the silence from which the pattern can be inferred. The Great Filter in its most disturbing form connects directly to a specific observational implication, sometimes called the Fermi observation or the Mars test. If you are looking for a sign that the Great Filter is ahead of humanity, the worst possible news would be finding life elsewhere in the solar system. Not complex life. Simple life. Microbial life. A bacterium on Mars. Think about that carefully. Think about why a positive result from a Mars mission would be in the same moment both one of the greatest scientific discoveries in history and a deeply troubling data point. If we found microbial life on Mars, it would mean that life emerged independently in two separate locations in the same solar system, that two planets in the same star system orbiting the same sun with roughly the same raw materials both produced self-replicating chemistry. The implication of that finding would be that life is not rare, that life does not require extraordinary circumstances. That life is what chemistry does when the conditions are right, and the conditions are right in many places. It would mean the early steps of the biological sequence, from chemistry to the first cell, from the first cell to the variety of microbial life, are not the filter. Those steps happen frequently. They are cleared easily. The filter is not there, and if those early steps are not the filter, then it is somewhere else. Later in the sequence. Somewhere between simple microbial life and the kind of civilization that can propagate itself across the galaxy. Somewhere in the part of the sequence that humanity is currently traversing. Every positive detection of life elsewhere removes a candidate for the early filter and pushes the filter later. If life exists on Mars, and in Europa's ocean, and in Enceladus's geysers, and in the clouds of Venus, that is 4 data points suggesting life is common and the filter is not in the early stages. Each such detection is extraordinary news and is simultaneously, through the logic of the Great Filter, unsettling news for where the filter might be located relative to our current position in the sequence. The better we become at detecting life, the more the filter moves toward our present. This is the specific thing that makes the search for extraterrestrial life in our solar system a complicated question for Fermi paradox researchers. Finding life elsewhere, finding simple life, common life, life that emerged independently in our own solar system, would mean that the step we thought might be the filter was not. And every step removed from the early part of the sequence is a step that pushes the filter toward us. The researchers who work on the Fermi paradox professionally describe a specific kind of dread associated with Mars missions and Europa missions and any search for life within our solar system. Not dread of what they might find, but dread of what finding it would imply about the Great Filter. A positive result from the search for extraterrestrial life in our own solar system would be, without question, one of the most important scientific discoveries in the history of humanity. It would be bigger than Copernicus, bigger than Darwin, bigger than any previous revision of our understanding of our place in the universe. It would confirm that life is not a unique accident of Earth-specific history. It would demonstrate that chemistry produces biology wherever the conditions allow. It would transform the expected number of inhabited worlds in the galaxy from a speculative number derived from unconfirmed assumptions into a lower bound derived from observed frequency. And it would make the Fermi paradox sharper, not softer, because the question of where the older civilizations are would become more urgent, not less. And simultaneously, it would be one of the most troubling data points imaginable for the Fermi paradox. Because if life arose independently on Mars, that means life arising is not the Great Filter. If life arose in the oceans of Europa or Enceladus, that means life arising is very common. And if life arising is very common, the filter must be somewhere else. Later, further along the path, closer to where we are, the more we remove early candidates for the Great Filter by finding evidence that those steps are common, the more the filter is pushed toward the present, and the present is where we are. Every scientist who works seriously on this question understands the logic. A positive biosignature from Mars, or from any body in our solar system, would be extraordinary news and quietly terrifying news at the same time. It would mean you are still approaching the filter. There is a resolution to the Fermi paradox that has the quality of feeling like an answer right up until you examine it carefully, and then falls apart. It is called the zoo hypothesis. The idea is that other civilizations exist and are aware of us, but they are choosing not to contact us. We are being deliberately kept in isolation, either because they are following some kind of non-interference protocol, like the Star Trek Prime Directive, or because they are studying us, or because they consider us too primitive to be worth the contact, or because contact would be harmful to our development. The zoo hypothesis has a certain intuitive appeal. It imagines the silence as the product of a thoughtful decision rather than the product of absence. But it has a critical flaw. For the zoo hypothesis to work, it requires that every intelligent civilization in the galaxy agrees on the same policy and enforces it consistently over all time. Not most of them, not almost all, every single one. Every civilization that has ever developed to the point of being capable of interstellar contact must have made exactly the same choice to maintain non-contact with Earth. and must have enforced that choice without exception. This requires a uniformity of behaviour across entirely independent civilizations that emerged from completely different evolutionary histories on completely different planets under completely different physical and chemical conditions, with completely different biologies, different cultural developments, different values, and different perspectives on what the right thing to do is. They all made the same call, every time, without exception. Consider how unlikely this is even within humanity alone. We are a single species from a single planet with shared biology, shared evolutionary pressures, and thousands of years of accumulated cultural exchange. We cannot agree on fundamental questions about how to organize societies, what counts as a moral action, or what the long-term priorities of our civilization should be. Different human cultures have reached different conclusions about the most basic questions of ethics and governance throughout history. Now extend this to civilizations that share none of our biology, none of our evolutionary history, and none of our cultural context. The idea that every one of them, independently and without coordination, arrived at exactly the same conclusion about non-interference with Earth and maintained it without a single exception across all time, requires an explanation more extraordinary than the phenomenon it attempts to explain. The zoo hypothesis also does not account for the ancient civilizations that would predate any such policy. Even if every civilization that exists right now agreed to non-contact, what about civilizations that existed 1 billion years ago, when Earth was still in the middle of its microbial phase? Did they adopt the same policy? How? And if they did not, where are the traces they left? There is also the defector problem. In any group decision, there is always pressure from individual members who calculate that defecting from the group norm is advantageous for them. If one civilization among thousands decides that contact is beneficial or interesting or simply worth trying, the uniformity breaks down. The zoo hypothesis requires that no civilization in the galaxy's history has ever been curious, or rebellious, or simply different enough to make a different choice. The silence cannot be explained by universal agreement among parties who have never met, and who have no mechanism to coordinate. An explanation has to account for why no civilization, across all of galactic history, has left a trace that we can detect. The most common response to the Fermi paradox when it is first encountered is the distance argument. Space is simply too vast for any signal to have reached us yet, or for any civilization to have expanded far enough to make contact. This argument feels intuitive. Space is enormous. Even at the speed of light, the nearest star is more than 4 years away. The galaxy spans 100,000 light-years. Even a signal travelling at light speed from the other side of the galaxy would take 100,000 years to reach us. If civilizations are spread thin across the galaxy and each is broadcasting for a finite time, the chances of a signal reaching us from the right direction at the right time seem slim. But the distance argument, while it sounds reasonable, fails to account for the age problem. The galaxy is not 100,000 years old, it is 13 billion years old. Stars have been forming, planets have been cooling, and chemistry has been running for 13 billion years. If a civilization emerged around one of the older sun-like stars in the galaxy, it had a multi-billion year head start on us. Multi-billion, not just a few million. What can you do with 1 billion years of technological development? We genuinely have no framework for answering this question honestly. The honest answer is, we do not know. We have had roughly 10,000 years of cumulative technology and 200 years of industrial technology. In those 200 years, We went from horse-drawn vehicles to landing probes on Mars, from quill pens to quantum computers, from bloodletting to gene editing the human genome. The trajectory is not linear, it is accelerating. Projecting this trajectory forward by a factor of 10 million, which is what 1 billion years of additional development would require, is simply not possible with our current conceptual tools. The answer is not more of the same, it is something categorically different. A civilization 1 billion years old is not a civilization with better rockets. It is something incomprehensible, operating at scales and in ways that are beyond our ability to anticipate, and something operating at that scale would leave traces that survive for millions of years, that propagate across the galaxy, that are visible from enormous distances. The distance argument also underestimates what physics allows even with technology much closer to ours. A civilization does not need to travel at the speed of light to colonize the galaxy. Probes traveling at 1% of light speed could reach the nearest star in 400 years. Probes that replicate themselves using material from the destination star system, then send new copies to the next star, would expand exponentially. The math shows that starting from one star, a network of self-replicating probes traveling at 1% of light speed could cover the entire galaxy in roughly 10 million years. 10 million years. In a 13 billion-year-old galaxy, this is less than 1/10 of 1% of the galaxy's age. The galaxy has had time for this process to have completed, from any sufficiently early starting point, many times over. If one civilization launched this network 5 billion years ago, the galaxy would have been fully covered before Earth's continents began forming. The distance argument says we might not have heard yet, because signals take time to cross the galaxy. The age argument says if anyone were out there and was producing signals or structures 1 billion years ago, that would have been more than enough time for evidence to reach us. The two arguments operate on different timescales. The distance argument is valid for civilizations that emerged recently, within the last few million years. For those civilizations, the light travel time and the expansion timescale are genuinely relevant. Signals and probes have not had time to reach us yet. But these recent civilizations are a small fraction of the possible population in a 13 billion-year-old galaxy. The vast majority of the history in which civilizations could have existed is in the deep past, and from the deep past there is no distance argument. A civilization that existed 5 billion years ago in this galaxy has had 5 billion years for its signals to reach us, and 5 billion years for its probes, if it built them, to explore every star system in the Milky Way multiple times over using only physics that is plausible extensions of current understanding. The Fermi paradox is not primarily a question about recent civilizations, it is a question about ancient ones. Where are the civilizations that existed 5 billion years ago? 1 billion years ago? Even 100 million years ago? They should have had time to fill the galaxy and make themselves undeniable. They did not. One of the most technically precise and logically tight contributions to the Fermi paradox debate was proposed by astronomer Michael Hart in a 1975 paper and developed further by physicist Frank Tipler into what is sometimes called the Hart-Tipler argument, or the Fermi-Hart paradox. The argument works from a specific and testable calculation. If a civilization wanted to explore or colonize the galaxy and it had a sufficiently long time horizon, it could accomplish this goal using technology that is a straightforward extension of current engineering rather than requiring any physics-defying capabilities. No faster than light travel is required, no exotic matter, no warp drives, nothing beyond what plausible extensions of near-future technology might achieve within the next few centuries. What is required is a specific type of technology that is a plausible extension of current robotics and manufacturing, self-replicating robotic probes. A probe that can travel between star systems at a modest fraction of the speed of light, perhaps 1 to 10%, using something like nuclear pulse propulsion, electromagnetic acceleration, or solar sail technology scaled up from current engineering concepts. A probe that, upon arrival at a new star system, uses the available raw material in the asteroid belt and outer solar system of that destination to manufacture copies of itself using automated fabrication technology that is already conceptually within reach. Each copy then departs for another star system, and the process repeats. This is the critical element, the self-replication. Without it, the process is linear and slow. With it, the process is not just additive but exponential. 2 probes become 4, 4 become 8, 8 become 16. Exponential growth over millions of years produces numbers that dwarf any human intuition. After 60 doublings, the count exceeds 1 quintillion. Each star in the galaxy could have multiple probes exploring its system before the process has run for even a small fraction of the available time. The original probe sends 2 copies. Those 2 copies each send 2 more, for a total of 4. Those 4 produce 8. 8 produce 16. The coverage grows exponentially across the galaxy. The Mathart-Tipler-Ran shows that at 1% of the speed of light, which is far below what some proposed propulsion systems could achieve, and is perhaps achievable within centuries of engineering development from our current position, accounting for travel time between stars and replication time at each destination. A single probe network launched from one civilization could cover the entire Milky Way galaxy within roughly 10 to 100 million years. The range depends on assumptions, but even the pessimistic end of the range is short compared to galactic history. The specific number depends on assumptions about travel speed, replication time, and what fraction of nearby stars are visited. But the result is consistently in the range of tens to hundreds of millions of years. The galaxy is 13 billion years old. Any civilization that launched this kind of probe network even 2 billion years ago would have completed galactic coverage roughly 50 times over by now. The probes would not just have passed through the solar system once. They would have had time to study every planet and moon in detail, leave detectable artifacts, return data to the originating civilization, and complete many additional cycles of expansion before today. The Hart-Tipler argument makes the Fermi paradox considerably harder to explain away, because it shifts the expected observable from electromagnetic signals to physical presence. Radio signals require pointing in the right direction at the right time. Physical probe networks, given enough time, are simply everywhere. Radio signals can be missed. Physical probes cannot easily be missed if the probe network has had billions of years to explore and catalogue every star system in the galaxy. It is not just about signals. We should expect to find evidence of ancient robotic probes in the asteroid belt. We should find anomalous objects on the moon that do not have natural origins. We should find signatures in Earth's geological record of visits millions of years ago. The absence of such evidence, as our ability to search the solar system improves, is significant. We have found nothing that requires such an explanation. This constrains the possible resolutions severely. Either the Hart-Tipler argument is wrong in some critical assumption, or no civilization has ever achieved the technological level needed to launch such probes, or no civilization has ever wanted to expand in this way, or every civilization that developed this capability was prevented from completing the process. Each of these alternatives carries its own specific implications for how to think about the future of technological civilizations, including ours. There is a category of resolution to the Fermi paradox that does not rely on civilizations being extinct or rare. It relies on civilizations being changed in a direction that makes them invisible to us. The idea is sometimes called the transcension hypothesis, developed most systematically by researcher John Smart. It proposes that as civilizations advance technologically, they do not expand outward into physical space. They expand inward into the very small. They miniaturize their technology and their computing infrastructure to operate at smaller and smaller physical scales with greater and greater efficiency. The trajectory of technological progress, Smart argues, points consistently towards smaller, denser, faster systems rather than larger and more expansive ones. Integrated circuits replaced room-sized computers. Smartphones replaced mainframes. Each generation of computing is smaller and more powerful than the last. Extended to its logical conclusion over millions of years, this trajectory leads to civilizations that have compressed their entire technological and computational existence into volumes far smaller than anything we associate with a civilization. Not spreading across planets and star systems, but concentrating into increasingly efficient structures at molecular or atomic or subatomic scales. The endpoint might be a civilization operating at the scale of a small room, or a particle physics experiment, or something we have no analogy for, doing things with the fundamental physics of spacetime that we have not yet discovered is possible. If advanced civilizations follow this trajectory, they become invisible to macroscopic astronomical surveys of the kind we conduct. We are looking for large-scale structures, radio signals propagating across light years, infrared excesses from stellar engineering. These are the signatures of a civilization at roughly our level or somewhat beyond it. A civilization that is still operating at planetary and stellar scales. We would have no ability to detect a civilization that has chosen to operate at nanometer or femtometer scales, consuming very little energy in macroscopic terms, producing no radio signals and no stellar modifications. They are not in the stars. They are not in the space between stars. They are inside matter itself, in scales of physical reality we have barely begun to explore, and that our current instruments cannot survey for signs of intelligence. The transcension hypothesis offers a universe full of civilizations that are present but not visible by any method we currently have, doing things we cannot currently imagine, operating in a domain of physics that we have not yet accessed. Whether this is a resolution or a description of a universe permanently beyond our ability to understand is itself an open question. The transcension hypothesis has a certain mathematical elegance. It does not require civilizations to destroy themselves. It does not require them to agree with each other on non-contact. It proposes a direction of development that might be inherently attractive: greater capability with less resource consumption, more computation in less space, deeper engagement with the fundamental structure of reality rather than shallow spread across its surface. But it is difficult to evaluate because it is difficult to falsify, and like other universal behavior explanations, it requires that this trajectory applies to every civilization without exception. No civilization in 13 billion years of galactic history has ever combined inward transcension with any outward expansion at all, not even a minimal presence, not even a single probe sent to a neighbouring star. That is a strong claim about the behaviour of all possible minds that have ever existed. The transcension hypothesis also has the property that if it is correct, we might be approaching a similar transition ourselves. The rapid miniaturization of computing, the increasing interest in quantum systems, the development of nanotechnology and molecular biology as engineering disciplines. All of these might be early steps in a trajectory that leads somewhere fundamentally different from the space colonization future often imagined. Whether that destination is a kind of transcension that makes a civilization undetectable, or something else entirely, is a question that belongs more to philosophy than to current science. The solution that researchers find most consistent with the available evidence and most disturbing in its implications involves the concept of civilizational longevity. Return to the Drake equation. The final variable is L, the average length of time a civilization remains capable of and interested in communicating. If L is very short, the number of detectable civilizations at any given moment is small even if civilizations form frequently. Humanity has been producing radio signals detectable from interstellar distances for roughly 100 years since the early days of radio broadcasting. 100 years in a 13 billion-year-old galaxy is nothing. Our window of detectability, if it closed tomorrow, would represent roughly 100 billionth of the galaxy's age. From the perspective of a distant observer looking for civilizations, we would be almost invisible even at our peak. If L is short for most civilizations, the galaxy could be full of civilizations that have each risen and fallen, with their windows of detectability so brief that the chance of two civilizations overlapping in time is very low. Ships passing in the night, each visible for only a moment. But this resolution only partially explains the silence. It explains the silence in terms of active communication. It does not explain the absence of structures. A civilization that rose and fell could still leave behind megastructures, orbital installations, modified star systems, something durable. Unless the civilizations that rise and fall do so completely, leaving nothing behind that lasts. Unless collapse is total. There are resolutions to the Fermi paradox that involve the nature of reality itself rather than the properties of civilizations within it. The simulation hypothesis proposes that our observable universe may itself be a computational simulation running on hardware belonging to a more advanced civilization. If this is true, the Fermi paradox dissolves in a specific way. Other civilizations are absent because the simulation was not designed to include them, or their signals are not rendered in regions we can observe, or the simulation is running at low resolution outside our immediate neighborhood. The simulation hypothesis is interesting philosophically and has been developed rigorously by thinkers including philosopher Nick Bostrom, who argued that at least one of three statements must be true. Either civilizations almost never reach the computational capacity to run detailed simulations, or civilizations that reach that capacity choose not to run them, or we are almost certainly inside a simulation. But as a resolution to the Fermi paradox, it explains too much. Any observation, including the silence, is compatible with it. An explanation that fits all possible observations equally well cannot be falsified, and cannot therefore be used to narrow the possibilities. More physically grounded is the cosmic timing argument. The universe has been producing sun-like stars for roughly 10 billion years. But the earliest stars were deficient in heavy elements, because heavier elements are produced in stellar interiors and distributed by supernova explosions, a process that requires multiple stellar generations. Rocky planets require carbon, silicon, iron, and other elements that were not abundant until the second or third generation of stars formed several billion years into galactic history. This places the earliest plausible rocky planetary systems at perhaps 9 to 10 billion years ago, only a few billion years before Earth itself formed. If intelligence requires billions of years to emerge from the origin of life, the first technological civilizations may not have emerged until within the last few billion years, reducing the head start available to earlier civilizations. But the timing argument also has limits. Even if the first possible technological civilizations emerged only a billion years before us, that is a billion years of development time. The Hart-Tipler expansion timescale is tens of millions of years. A billion-year head start is 60 repetitions of the time needed to fill the galaxy. Neither timing nor simulation fully resolves the paradox. They soften it. They raise the possibility that the silence is not deeply significant. But they do not eliminate the basic question: where are the traces of anyone who came before us, from any time, in any form? There is a class of explanation that does not require civilizations to be rare or short-lived. It requires them to be hiding. The dark forest hypothesis, named after a novel by Chinese science fiction author Liu Cixin, proposes that the universe is actually full of intelligent life, but that every civilization has arrived at the same conclusion through logic, and that conclusion is: do not reveal yourself. The argument works like this: every civilization needs resources to survive. Resources in the universe, while vast, are finite. Any two civilizations that become aware of each other are potential competitors for those resources. You cannot fully trust a civilization you have never met, whose evolutionary history, values, and long-term intentions are entirely unknown to you. You cannot verify any communication they send. In any interaction between civilizations with no shared history, no common culture, and no enforcement mechanism, the outcome ranges from neutral to catastrophic, depending on the other party's intentions, and you have no reliable way to determine those intentions from a radio signal. Given this uncertainty, the argument runs: the rational strategy is silence. Reveal your existence, and you attract attention from parties whose motives are unknown. Silence eliminates the exposure. Silence is survival. And further, if silence is the rational strategy, then any civilization that breaks silence may be either ignorant of the risk or accepting the risk for some reason. Either way, from the perspective of other civilizations, a broadcasting civilization might be seen as either naive or dangerous, and the rational response to detecting a naive or dangerous civilization is to eliminate it before it can pose a threat. The dark forest hypothesis is disturbing because it does not require civilizations to be evil. It requires them to be rational under conditions of deep uncertainty. Rational agents who cannot verify the intentions of other agents and who face potentially existential competition may arrive at the same defensive posture: strike first or remain hidden, because being second has no recovery. If the dark forest is real, we have been broadcasting our existence into it for 100 years. We sent a message called the Arecibo message in 1973. We have sent multiple other intentional signals since. The Voyager probes carry physical maps to our location. We have been advertising ourselves to a potentially dangerous universe. The dark forest hypothesis does not have strong evidence for or against it. It is a logical argument rather than an empirically derived one, but it has the quality of being consistent with the evidence we have. It explains why the universe is silent, even if it is full of life. It explains why we see no signals. It does not explain the absence of megastructures, unless civilizations are also careful to build in ways that do not reveal their presence. One resolution to the Fermi paradox that does not involve catastrophe or rarity is the argument that the universe has a habitability window and we may be near the beginning of it. The early universe in the first few billion years after the Big Bang was not hospitable to complex life. The first stars were made almost entirely of hydrogen and helium because heavier elements had not yet been forged in stellar interiors and distributed by supernova explosions. Without carbon, oxygen, silicon, iron, and the other heavy elements, rocky planets cannot form. Without rocky planets, and likely without liquid water and the chemical versatility of carbon, life as we understand it cannot emerge. The first generation of stars had to live and die, seeding the galaxy with heavy elements, before the second generation of stars could host rocky planets. Then those planets had to cool and develop water and chemistry. Then life had to begin and evolve over geological timescales. All of this takes time, several billion years at minimum. This means that the earliest possible technological civilizations in the Milky Way probably emerged somewhere in the range of 5 to 10 billion years ago, and that assumes very rapid evolution. If intelligence requires something close to Earth's timeline of roughly 4 billion years from life to technology, the first technological civilizations in the Milky Way may have emerged only 1 billion or 2 billion years before us. This reduces the head start available to earlier civilizations. 1 billion years instead of 13 billion. The Fermi paradox becomes less acute if the window for technological life is narrow enough, and if civilizations are rare enough that the expected number of civilizations with very large head starts is genuinely small. But even 1 billion-year head start is enough to fill the galaxy with probe networks many times over. But there is a further element. The universe is not becoming less hospitable to life. It is becoming more hospitable. The rate of star formation peaked early in the universe's history, but has been declining. The total amount of heavy elements in the universe, which are produced in stellar interiors and distributed by supernovae, is growing over time. Future generations of stars will be richer in heavy elements than current ones. Future rocky planets will have more of the ingredients for complex chemistry. The universe in the far future may be more hospitable to life than the universe today. This means we may be living at an early point in the universe's life-bearing history. Not the earliest, but early. If the vast majority of civilizations that will ever exist in this universe have not yet emerged, the universe today would indeed be quiet. Not because life is doomed, but because the galaxy has not yet had time to fill up. This interpretation does not easily account for the Hart-Tipler argument's implication that even a small number of early civilizations should have expanded to fill the galaxy by now. If any civilization in the last 5 billion years was long-lived and expansionist, we should see evidence of it. The cosmic window argument does not fully explain why there is no such evidence, unless civilizations are also consistently short-lived, which returns to the longevity question. But the argument does reframe the silence in a potentially hopeful direction. If civilizations are rare and recently emerged, and if most of them survive their critical period and go on to become long-lived and expansive, the galaxy may be on the verge of becoming populated for the first time in its history. The silence we hear now may be the silence before the first conversations, not the silence after everyone who tried has stopped speaking. Which interpretation is accurate depends entirely on what happens to civilizations during the critical period we are currently in. When people claim the universe is silent, it helps to be precise about what we have actually searched, because the search so far is far more limited than most people realize. The systematic search for extraterrestrial radio signals began in 1960 when Frank Drake, the same Drake who would design the Arecibo message 14 years later and formulate the Drake equation, pointed the Green Bank radio telescope at two nearby Sun-like stars, Tau Ceti and Epsilon Eridani, and listened at the hydrogen emission frequency for several weeks. He heard nothing, or rather, he heard a brief apparent signal that turned out to be a military aircraft using a classified frequency. He called the project Ozma, after the Queen of Oz in L. Frank Baum's books, a land far away and difficult to reach. It was the beginning of a 60-year search. Since then, SETI has grown enormously in scope and sensitivity. The most comprehensive modern search is the Breakthrough Listen program. Launched in 2015 with $100 million of funding, which uses some of the world's largest radio telescopes to survey millions of stars across billions of radio frequency channels. By some measures, Breakthrough Listen has performed more SETI observations in a few years than all previous SETI programs combined. And yet, the fraction of the observable universe that has been searched is tiny. We have examined a few thousand stars with serious radio telescope sensitivity. The Milky Way contains 100 to 400 billion stars. We have looked at a fraction of 1% of the stars in our own galaxy, and we have not examined most of those at many frequencies for long periods of time. We have covered an even smaller fraction of the possible frequency space, the number of radio frequencies that could conceivably carry a signal. We have also been searching for only about 60 years, a blink in the context of the question. If a civilization broadcasts for 10,000 years, there is roughly a 1 in 200 chance we would be searching during the overlap period, even if we pointed our telescopes at exactly the right star. And we have been searching almost exclusively in the radio band. A civilization that evolved past radio communications technology 1 million years ago would not be producing the signals we are looking for. They might be using tightly directed laser pulses. They might be using quantum communication methods we have not invented. They might have found ways to encode information in physical substrates that we cannot detect with any instrument we currently possess. The silence so far is a null result in a limited search. It constrains the possibilities without eliminating them. It reduces the probability of certain kinds of signals from certain kinds of civilizations at certain distances and frequencies. It does not prove that the universe is empty. It proves only that the specific kind of civilization we are looking for, one that broadcasts widely and persistently at frequencies we monitor, is not abundant within the fraction of the galaxy we have examined with the sensitivity we have achieved. This distinction matters for how we interpret the silence. A thorough search that found nothing would be more significant than a preliminary search that found nothing. Our current search is closer to preliminary than thorough. Future searches will be substantially more sensitive and comprehensive. This does not solve the Fermi paradox, because the Hart-Tipler argument about physical expansion and the megastructure surveys are not constrained by the limits of radio telescope sensitivity. A Dyson sphere signature is not a radio signal. A probe in our asteroid belt would be findable with our current instruments if we conducted a systematic search. These are macroscopic physical objects, not narrow-band signals that could be missed by pointing in the wrong direction. The absence of macroscopic evidence is harder to explain by appeal to the limits of our search, but the honest accounting of what we know from radio searches specifically is this. We have checked a small part of the sky for a brief time at a limited range of frequencies using methods calibrated to the technology of our current stage of development. We have found nothing so far. The question of what that means depends heavily on how you weigh the scope of the search against the theoretical expectation of what should be there. astronomers have looked for megastructures. The concept of a megastructure in the context of the Fermi paradox comes from physicist Freeman Dyson, who in 1960 proposed that a sufficiently advanced civilization would face an energy problem. As technology advances, energy needs grow. The ultimate energy source available to any civilization is its host star. A star like the Sun produces more energy in 1 second than humanity has used in all of recorded history. Capturing a significant fraction of that energy would require surrounding the star with collectors. Dyson proposed that a civilization might disassemble its outer planets and use the material to build a shell or swarm of collectors around the star, a structure now called a Dyson sphere or Dyson swarm. From the outside, such a structure would absorb most of the star's visible light and re-radiate it as heat at lower temperatures, in the infrared range. A Dyson sphere would therefore look like a star that emits much less visible light than expected for its size and spectral type, but emits an unusual amount of infrared radiation. It would have a specific observational signature. Astronomers have searched for such signatures. They found a candidate in 2015, a star called KIC 846852, known by the name Tabby's star after citizen scientist Tabitha Boyajian, who first noticed its anomalous behaviour in data from the Kepler Space Telescope. Tabby's star dimmed by up to 22% at irregular intervals, in patterns that could not be explained by a transiting planet or any known natural phenomenon. The dimmings were asymmetric, irregularly shaped, and unpredictable. The news media ran with the story. Megastructure, alien civilization, Dyson sphere under construction. Subsequent analysis found that the dimmings were consistent with asymmetric dust clouds, possibly from the breakup of a comet family. The alien megastructure hypothesis was ruled out as the most likely explanation, though not definitively disproved. Tabby's star remains an unusual object. Other surveys have searched systematically for Dyson sphere signatures across millions of stars. Nothing has been found that requires an intelligent explanation. No star in the observable galaxy shows the specific infrared excess and reduced visible output that would indicate a civilization harvesting its star's energy. The galaxy appears, to the best of our observational ability, to be devoid of ancient megastructures. If civilizations built them, the civilizations and their structures are gone. If civilizations never built them, either they never advanced far enough or they found a reason not to. The variable L in the Drake equation, the average longevity of a technological civilization, deserves its own examination because it connects the Fermi paradox directly to human history. Humanity has been producing radio signals that could theoretically be detected by a sufficiently sensitive receiver at interstellar distances for roughly 100 years. In the first few decades of broadcasting, the signals were not particularly powerful and would be difficult to distinguish from natural radio noise at even modest distances. But by the mid-20th century, high-powered military radar installations and powerful commercial television transmitters were producing signals that would be detectable by a telescope of Arecibo's sensitivity from within a few light-years of Earth. This means our window of detectability, the period during which we have been emitting signals that could in principle be identified as artificial by a distant receiver, is currently about 100 years old and expanding at the speed of light. Our radio bubble extends approximately 100 light-years into the galaxy. There are roughly a few thousand star systems within that bubble. The Milky Way is 13 billion years old. Our window is 0.0000008% of galactic history. If another civilization searched for us by pointing a radio telescope at the Sun during a random 100-year window in galactic history, the probability of overlapping with our current broadcasting period is vanishingly small. This simple arithmetic suggests that even a galaxy full of civilizations could appear mostly silent at any given moment if each civilization's window of detectable radio broadcasting is short relative to the age of the galaxy. Now scale this thought experiment. If the average technological civilization produces detectable signals for 1,000 years, and if there are 0,000 such civilizations active at any given time in the galaxy, the probability of detecting one at any random moment depends on how those windows are distributed. In 13 billion years of galactic history, 1,000 civilizations, each lasting 1,000 years, would produce a total of 1 million years of detectable signal, out of 13 billion years. The coverage is 0.008% of time. On average, at any given moment, only a small number of civilizations would be broadcasting, and they would be spread across a galaxy of 100 billion stars. If L is long, the paradox is acute, long-lived civilizations would have time to fill the galaxy and would still be there when we look. If L is short, most civilizations pass through the window quickly and the galaxy is never occupied by many at once. The question that matters is why L might be short for the typical civilization. What stops civilizations from persisting long enough to be detectable? There are multiple possible answers, and they are not mutually exclusive. Civilizations might be short-lived for completely different reasons than each other, with the aggregate result being a low average L regardless of which specific cause dominates. One is the self-destruction scenario. Civilizations acquire the capability to destroy themselves before they develop the social and governance structures to prevent that destruction, and most of them fail to navigate the gap. Another is simply that civilizations change in ways that make interstellar communication less appealing or less likely. Not death, but transformation into something that does not broadcast in the way we expect. A third is that civilizations go inward rather than outward, the transcension hypothesis, focusing on computing and virtual experience rather than physical expansion. Each of these would produce a short L for detectable signals of the kind we search for, and any of them, if common, would explain the silence. The self-destruction scenario is the most alarming because it has specific implications for us. If the typical value of L is short because civilizations tend to fail at the point of mastering their own dangerous technologies, the question becomes, why do they fail? And that question is a direct question about the trajectory of civilizations at the specific moment when they become dangerous to themselves. We are at that moment, not metaphorically. Literally, we are currently navigating the development of weapons of mass destruction, engineered biology, and artificial intelligence at the same time that we are becoming aware, for the first time, that these technologies could end us if managed badly. The gap between when a civilization develops civilization-ending capability and when it either manages that capability successfully or fails is probably a period of decades to centuries, not millennia. If most civilizations fail in that window, L is short. If most succeed, L is long, and the Fermi paradox becomes acute again. The Fermi paradox, viewed through the lens of L, is asking a question with direct implications for us. Which side of the filter are we on? Did the difficult step happen before we arrived here, making our future at least potentially open? Or is the difficult step the one we are approaching now, the one that the silence suggests most civilizations do not navigate successfully? The Tabby star episode deserves more examination than it usually receives, because it illustrates both how we search for megastructures and how the inference from anomalous observation to extraordinary explanation should work. KIC 846285, the star in question, was identified in data from the Kepler Space Telescope by citizen scientists working through the Planet Hunters project, which enlisted volunteers to visually inspect Kepler's light curves, looking for the characteristic dip in brightness that indicates a planet passing in front of the star. Planets produce small, regular, symmetric dips. What the volunteers noticed in KIC 846285 was different, irregular, asymmetric dimmings of various depths, with the deepest reaching 22% of the star's normal brightness. For context, a Jupiter-sized planet transiting a Sun-like star causes a dimming of roughly 1%. Something blocking 22% of the light from a star is not a planet. Even a gas giant the size of Jupiter would not dim the star by that amount. The dimmings were also irregular, occurring at different intervals with different durations and depths. Regular periodic behavior is the signature of an orbiting object. Irregular behavior suggests something else, possibly a cloud of material, possibly multiple structures at different orbital distances. The researcher who investigated the star most extensively, Tabitha Boyajian, initially entertained a megastructure hypothesis not as a serious scientific conclusion, but as one of several options to be ruled out. The most popular science reporting seized on it, and the star became famous under the name Tabby's star. The original scientific paper listing possible explanations was much more cautious. Subsequent multi-wavelength observations detected that the dimming was wavelength dependent. The star dimmed more at shorter wavelengths of light than at longer ones. This is a strong indicator of dust rather than solid structures. Dust absorbs blue light more efficiently than red light, producing a characteristic reddening effect. A solid megastructure would block all wavelengths equally. The wavelength-dependent dimming strongly argued for dust clouds rather than constructed objects. The most likely current explanation involves dust from an ongoing collision or fragmentation event in the star's inner solar system, possibly cometary material or the remains of a disrupted larger body. This is not yet definitively confirmed, but it is consistent with the observations and does not require any exotic physics or biology. The Tabby star episode illustrates the correct scientific response to anomalies. Take them seriously enough to investigate thoroughly, list all possible explanations including the extraordinary ones, and then systematically test each against the available data. The megastructure hypothesis was not ridiculous to consider. It was a legitimate scientific hypothesis that fit the initial data. It was ruled out by additional, more detailed observations. That is how science is supposed to work. The episode also illustrates something about the sociology of the Fermi paradox search. The megastructure hypothesis attracted enormous public interest and media coverage. It raised the possibility of a genuine detection of alien intelligence, and the public and press responded with excitement. The more mundane explanation, cometary dust, attracted much less attention when it emerged. This asymmetry between the excitement of a positive result and the relative quiet of a negative one is a recurring pattern in the search for extraterrestrial intelligence. The null results accumulate without fanfare. The anomalies get headlines even before they are understood, and the corrections rarely receive the same coverage. Beyond individual anomalies, systematic searches for megastructures have been conducted across large samples of stars. A 2015 study using data from the Wide Field Infrared Survey Explorer, WISE, searched 100,000 galaxies for the extreme infrared excess that would indicate a Kardashev Type 3 civilization, one that has captured the energy output of an entire galaxy. None were found that could not be explained by known astrophysical processes. A similar search of millions of individual stars for Dyson's sphere-like infrared excess found no candidates that held up to follow-up examination. The universe, to the limits of current observation, appears to contain no megastructures in our cosmic neighbourhood. No ancient civilizations have modified the stars they orbit in ways that produce detectable infrared excesses or anomalous dimming patterns that require intelligent explanation. This is a significant null result. It constrains the frequency of long-lived, energy-hungry civilizations in our observable region of the universe. Either civilizations that could build at this scale never existed, which means intelligence is rare or short-lived, or they existed but chose not to build in ways that leave thermodynamic signatures, which requires explaining why all of them made the same unusual choice. Or they built such structures long ago and dismantled them, and we happen to live in an era when none are currently operating. Or they built them in ways we cannot detect with current instrumentation. Each alternative has implications for what the silence means about the trajectory of civilizations. There is a resolution that is almost too uncomfortable to speak plainly. It is the possibility that the Fermi paradox is not a paradox at all, because the calculation is correct and both sides of the equation are true, and the silence means what it appears to mean, that intelligence is consistently terminated before it can make itself known across the galaxy. The universe is old. Life may be common. Intelligence may emerge. Technology may follow. And then something happens. Not one thing. A convergence. The same convergence that any technological civilization eventually faces, regardless of the specific evolutionary path that produced it, because the convergence emerges not from the biology but from the physics of what becomes possible when intelligence and industry combine. Think about what the path from microbial life to a civilization capable of interstellar communication requires in terms of technological milestones. Chemistry that can sustain self-replication. Biology that evolves complexity over geological time. Nervous systems capable of modelling the environment. Language that enables cumulative knowledge across generations. Agriculture that frees population from immediate food production. Industry that enables mass production of complex tools. Nuclear physics that reveals the energy at the heart of matter. Electronics and computing that extend the power of the mind. Biological engineering that enables direct manipulation of life at the molecular level. Each of these developments is accompanied by new capabilities and new dangers. Industry brought fossil fuels and climate change. Nuclear physics brought energy and weapons capable of ending civilization. Biological engineering is bringing the possibility of engineered pandemics of arbitrary lethality. Computing and artificial intelligence are bringing capabilities whose alignment with human survival cannot be guaranteed. Every step up the technological ladder introduces new capabilities and new failure modes that grow proportionally with the power of the capability. The same nuclear physics that can power cities can destroy them. The same biological knowledge that enables medicine enables engineered disease. The same computational capabilities that could accelerate every field of human knowledge could, if the objectives of a sufficiently capable system are misspecified, pursue those objectives at scales and speeds incompatible with civilization's continuity. The failures at the high rungs of the ladder are not the recoverable failures of earlier technological stages. A civilization that develops nuclear weapons and uses them in total war does not return to the pre-nuclear era. The infrastructure, the knowledge, the distribution of weapons, none of it can be undone. A civilization that engineers a self-replicating pathogen that kills a majority of its population does not have a clear recovery path. A civilization that creates an artificial intelligence system, optimizing at high capability for objectives misaligned with its survival, does not receive a second attempt. The window between developing these capabilities and either mastering them or being destroyed by them may be short. Consider the nuclear case as a reference point. Humanity tested the first atomic bomb in 1945. Thermonuclear weapons capable of ending industrial civilization in sufficient numbers existed by 1952. The Cuban Missile Crisis, in which Soviet and American forces came to the edge of nuclear exchange, occurred in 1962. 17 years from first test to near use. The window from first acquisition to first near catastrophic use was less than 2 decades. The window from first acquisition to enough weapons for civilizational extinction was perhaps 1 decade. Decades, perhaps a few centuries, as now to bound. In a universe that is billions of years old, a civilization that exists for a few centuries and then ends leaves almost no trace. And this may be the pattern. Life emerges. Intelligence emerges. Technology emerges. The civilization reaches a bottleneck defined by the gap between their destructive capabilities and their wisdom. Most do not cross it. The silence of the universe may be the accumulated echo of thousands of civilizations that made it to this moment, this exact technological stage, and did not survive what followed. The pattern is invisible to those inside it, because you cannot see the filter from below the level where it operates. The filter is defined by the moment when capability exceeds wisdom, and that moment is not visible as a filter until after you have already arrived at it. Here is what makes the Fermi paradox different from other deep questions in science, and why it deserves to be taken more seriously than it typically is. Other deep questions in astrophysics and cosmology are about the past or the distant future, the age of the universe, the nature of dark matter, the conditions in the first seconds after the Big Bang, what happens at the singularity inside a black hole. These questions matter to our understanding of the universe. They are worth pursuing, but they do not have direct, immediate implications for whether humanity continues to exist. The Fermi paradox is different. The explanation that most coherently accounts for both the likely prevalence of intelligence and the complete absence of any detectable signal or trace is that technological civilizations are terminated early, before they can expand across the galaxy, by mechanisms that grow from the same technologies that make them technological civilizations in the first place. And we are a technological civilization, at precisely the stage where those mechanisms are developing. Whatever terminated the others, assuming that is the correct interpretation, is the same category of challenge that we are navigating now. The same nuclear weapons whose total destructive capacity is capable of civilizational collapse. The same biological engineering capabilities that grow more accessible each decade. The same artificial intelligence development whose trajectory we are only beginning to understand. The same gap between our capability to create powerful systems and our wisdom to use those systems in ways that remain compatible with long-term human survival. The Fermi paradox, if its most consistent interpretation is correct, is not just a question about astronomy or about what exists out in the universe waiting to be found. It is a question about the typical trajectory of civilizations that look like us, with our kind of biology and our kind of technology and our kind of challenges when they arrive at the stage we are at now. And the answer, inferred from the silence, is not comfortable. Most of them do not make it through to the stage where they become detectable across the galaxy. The silence is data. It is not merely data about abstract possibilities, It is not primarily data about the distant past of other civilizations. It is data about the pattern that civilizations like ours tend to follow. And that pattern, if the silence reflects it accurately, ends before interstellar detection is possible. We are inside the pattern. We are at the exact moment the pattern predicts is critical. Whether we are exceptional, whether we are the ones who understand the pattern clearly enough to avoid it, is not yet determined. That determination is being made in real time by the decisions of people alive right now. Not everyone agrees on this interpretation, and the disagreement matters, both scientifically and for how we think about our own situation. Some researchers argue that the silence tells us very little about individual civilizations, because we cannot observe them at the individual level with sufficient resolution or coverage. We see aggregate patterns across limited samples, not individual histories across the full galactic population. The absence of observable signals within our current detection capacity does not prove those civilizations died. It might mean they are communicating in ways our instruments cannot detect. It might mean they are not broadcasting outward at all, using directed communications rather than omnidirectional signals. It might mean they have moved beyond the kind of electromagnetic technology we associate with early industrial civilization to methods we have not yet invented. This is a valid scientific point. Our radio telescope searches have real limitations. We have covered a small fraction of the sky at a small fraction of frequencies for a short period. The universe is old enough that any civilization that survived for 1 billion years would likely have technology 1 billion years more advanced than ours, and predicting what that technology looks like from our current vantage point is approximately like asking a medieval scholar to predict quantum mechanics. But the argument has limits. Even granting that radio searches are incomplete and may be looking for the wrong signal, the megastructure searches are more robust. An infrared excess from a Dyson sphere-like structure is detectable with existing telescopes from thousands of light years away. It does not require knowing the specific communication technology used. It does not require pointing at the right star at the right time. It is a macroscopic modification of a star system that is visible to broad surveys. The absence of detectable megastructures in our surveys of millions of stars is harder to explain by appeal to our limited technology. Either no civilization has built at this scale in our observable neighborhood, or they built in ways that produced no detectable infrared excess, which would require building so efficiently that nearly no waste heat escapes to space. The silence is consistent with the proposition that technological civilizations do not persist long enough or spread widely enough to leave detectable macroscopic traces in our vicinity. It is difficult to reconcile with the proposition that the universe is full of long-lived, expanding civilizations, because the physical signatures of stellar engineering should be visible in large-scale astronomical surveys regardless of what communication technology those civilizations use internally. There is an observation about the Fermi paradox that rarely gets its full weight in popular discussions. The search we have conducted so far is not a comprehensive search, and the silence we have detected is not a comprehensive silence. The systematic search for extraterrestrial radio signals has been running for roughly 60 years. In the context of the question we are asking, a question about the products of billions of years of cosmic evolution, 60 years of searching is not a long time. We have covered a small fraction of the available frequency space, a small fraction of the sky, and almost no time at all in the context of cosmic history. The null result we have accumulated is important and constraining. It is not a definitive absence. It is a preliminary survey of a very large territory. New instruments will substantially expand the search. The Square Kilometre Array, when complete, will be the most sensitive radio telescope ever built, capable of detecting signals from much greater distances at much lower power levels. Future space missions designed for exoplanet atmosphere characterization may detect biosignatures, chemical disequilibrium in planetary atmospheres that would indicate ongoing biological activity on nearby worlds. The James Webb Space Telescope has already begun characterizing the atmospheres of planets orbiting other stars, and while the current results are focused on larger planets, future instruments may extend this to Earth-sized worlds. We are on the verge of being able to look for life in ways that were not possible even a decade ago. The next 20 to 30 years may substantially change what we know, either by finding signals or biosignatures that break the silence, or by placing much stronger constraints on the absence. If a signal is found, or a biosignature, or any unambiguous evidence of life beyond Earth, the Fermi paradox immediately sharpens into a new form. Not because the existence of life becomes more likely, we already believe it to be likely, but because the question of where the older civilizations are, the ones that had billions of years to develop and expand, becomes more pressing. If life is common, the silence of ancient technological civilizations becomes the specific thing that needs explaining. If we find simple microbial life, life that never reached intelligence, that too narrows the filter. It places the barrier somewhere between microbial life and complexity, or between complexity and intelligence, or between intelligence and technology, or between technology and long-term survival. Each detection moves the filter. If we find nothing, after decades of searching with increasingly sensitive instruments across large fractions of the sky, that too is data. Absence of evidence after a sufficiently thorough search does become evidence of absence. Every piece of data narrows the space of possibilities. The silence itself is data, and the data so far is consistent with a universe that is either mostly empty of technological intelligence, or one in which technological intelligence does not persist long enough to leave a detectable trace across the distances and timescales our current searches cover. In November 1974, humanity deliberately shouted into the silence. The Arecibo radio telescope in Puerto Rico, at the time the largest single-dish radio telescope in the world, was upgraded with new transmitters. To celebrate the upgrade, astronomers Frank Drake and Carl Sagan designed a message and broadcast it toward the M13 globular cluster in the constellation of Hercules, roughly 25,000 light-years away. The Arecibo message was 1,679 binary digits long, transmitted at a frequency of 2,380 MHz with a total power of 450 kilowatts. The number 1,679 was chosen because it is the product of two prime numbers, 23 and 73, meaning the message can only be meaningfully arranged into a rectangular grid of those specific dimensions. This mathematical structure serves as a self-evident clue about how to decode the message. Any civilization capable of receiving radio signals and doing basic number theory would recognize that 1,679 is the product of exactly two prime numbers, and would naturally try arranging the digits as a rectangular grid of those dimensions. Any civilization mathematically sophisticated enough to understand the transmission would understand that the grid arrangement is the key, and would decode the image contained within it. The image, once decoded, shows the numbers 1 through 10 in binary, the atomic numbers of the elements that make up DNA, the formulas for the nucleotides of DNA, a graphic of the double helix, a figure of a human being with a number indicating the human population, a graphic of the solar system indicating which planet the message came from, and a graphic of the telescope itself. The message will take 25,000 years to reach M13 at the speed of light. If anyone there receives it, decodes it, and responds immediately, the response will arrive on Earth in roughly 50,000 years. No civilization that sent the message will be alive to receive the reply. The globular cluster itself may not still contain the same stars in the same configuration by the time the signal arrives, due to the proper motion of stars within the cluster and the motion of the entire cluster through the galaxy. Drake and Sagan were not seriously expecting a reply in any human-relevant time frame. The message was partly symbolic, a demonstration of what the newly upgraded telescope could do, and a public statement of the search for extraterrestrial intelligence as a legitimate scientific endeavour. Drake himself later acknowledged that the message was more of an educational exercise, illustrating the challenges and possibilities of interstellar communication, than a genuine expectation of a reply within any human-relevant time frame. The message itself was designed to be decodable by any civilization with mathematics and physics knowledge, on the theory that these are universal features of any intelligence capable of receiving radio signals. Since the Arecibo message, a number of other intentional transmissions have been sent by various groups. These are sometimes called active SETI, or METI, for messaging extraterrestrial intelligence, to distinguish them from the passive listening of traditional SETI. In 1999 and 2003, messages called the Cosmic Call were sent from a Ukrainian radio telescope toward a set of nearby stars selected for their similarity to the Sun. In 2008, NASA transmitted a Beatles song toward Polaris as a symbolic gesture. A message called A Message from Earth was sent in 2008 toward the Gliese 581 system, about 20 light-years away, by a social network that had collected submissions from its users. Each of these transmissions represents a unilateral decision to announce our presence to a universe whose nature, with regard to whether other intelligences exist and what their intentions might be, remains entirely unknown to us. The dark forest hypothesis considers this potentially catastrophic if the universe contains civilizations that respond to broadcasts by eliminating the source. Then we have been inviting exactly that response for a century of unintentional broadcasting and several deliberate transmissions since 1974. Most researchers consider this unlikely to produce negative consequences given the distances and timescales involved, and there is genuinely no way to assess the probability without knowing whether other intelligences exist and what their dispositions are. We are making an irreversible decision in a state of deep uncertainty, because the signals have already been sent, that the decisions were made without global consensus, without international coordination, without systematic consideration of the risks. This is itself a symptom of the kind of coordination gap that the Fermi paradox's most uncomfortable interpretation predicts will characterize the critical period in a civilization's development. The decision to broadcast our presence to the universe was not made by humanity. It was made by a handful of scientists at a handful of institutions. There was no global debate. There was no international framework for evaluating the risk. There was no consensus among governments, philosophers, or the general public. A few individuals decided, and then it was done. The same pattern appears in the development of nuclear weapons. A few thousand scientists and engineers, working at the direction of one government, developed civilization-ending weapons in less than 4 years. No global framework existed for governing their development. None has been fully developed since. The capability exists. The governance does not match it. The same pattern is appearing with biological engineering and artificial intelligence. The capabilities are developing rapidly. The governance frameworks lag significantly behind. Decisions that may have civilizational scale consequences are being made by small groups of people without global coordination or consensus. If this pattern is universal, if every technological civilization faces this same gap between what it can do and what it has agreed on doing, the Fermi paradox's darkest answer becomes more plausible rather than less. The silence from M13 will not arrive for another 24,900 years. We will not know for a very long time whether the shout was heard or whether being heard was advisable. Step outside on a clear night and look at the sky. The stars you see are close, by galactic standards. The nearest are a few light years away. Alpha Centauri, 4 light years. Sirius, 8 light years. The farthest you can see with the naked eye are perhaps a few thousand light years away, still a tiny fraction of the galaxy's diameter. Beyond those stars, the galaxy continues for another 50,000 light years to the far edge, densely populated with stars similar to our Sun, most of which we now know host planets, many of which host rocky planets in habitable zones. And beyond our galaxy are hundreds of billions of other galaxies, each with hundreds of billions of stars, each with their own billions of years of history. The silence in that sky is not natural. It is not what the math predicts. The math predicts voices. The math predicts structures that can be detected from thousands of light years away. The math predicts that a universe this old and this large, with chemistry this productive and time this abundant, should have generated something that makes itself known. Something should be out there. The silence does not mean nothing. Absence is not emptiness. Absence is data, and the data is consistent with a specific interpretation. Maybe we are the rare exception. Maybe the silence is simply the sound of a galaxy that produces intelligence almost never, where Earth is an unlikely convergence of conditions so specific that it may not have been repeated anywhere within detection range. Maybe the silence is the sound of a mostly empty universe. Maybe we are early. Among the first technological civilizations in a galaxy that will eventually, over billions of years, fill with minds of various kinds. The silence is not tragedy, it is timing. We are the vanguard, arrived before the rest. Maybe the civilizations are there and are choosing silence. The dark forest, every intelligence independently arriving at the conclusion that revealing itself is a mistake, and the universe falling quiet as a result of 10,000 independent conclusions converging on the same answer through pure logic rather than coordination. Or maybe the silence is a pattern, a repeating one, the same thing happening over and over again to every civilization that reaches the point we are at now, not because of any external force, not because the universe is hostile, because the capabilities that define a civilization as technological also define the mechanisms by which it can end itself. And the gap between acquiring those capabilities and developing the wisdom to manage them is a gap that most civilizations do not cross. We are a young civilization by any galactic standard. We have had nuclear weapons for less than a century. We have been globally connected for less than a century. We have been seriously aware of the scale of our environmental impact for about 50 years. We are beginning to develop artificial intelligence whose trajectory is not fully understood even by those who build it. We face coordination challenges, climate, inequality, political instability that require levels of global cooperation we have not yet demonstrated. We are at exactly the moment that the Fermi paradox, in its most consistent interpretation, predicts is where the pattern plays out. Not in the far future. Not after some distant threshold has been crossed. Now, in this century, in the next few decades, in the decisions being made by people alive today. At the moment when the tools that define us as a technological civilization are reaching the scale at which they can determine whether we continue or not. The silence of the universe is not peaceful. It is not the comfortable silence of an empty room. It is a silence with a shape, and the shape suggests a pattern. A distribution. A population of civilizations that reached a certain stage, and a distribution of outcomes at that stage, and the distribution is heavily weighted toward the outcome that does not produce a detectable presence. A warning encoded in the only language that crosses interstellar distances without requiring a specific receiver, a shared frequency, or any prior contact between sender and recipient, the absence of any voice that survived long enough and spread far enough to be heard across the gulf. Absence as signal. Silence as message. The pattern visible only to those who know to look for it, who understand what the math predicts the expected count should be, and who are willing to sit with what the gap between the prediction and the observation might mean. Every civilization that came before us either did not reach this stage at all, because the early biological steps were too improbable, or passed through this stage in a way we cannot detect, because they became invisible rather than extinct, or did not survive this stage because the gap between capability and wisdom is a gap that most civilizations do not cross. We do not yet know which category we will fall into. That determination is not made by the universe. It is not made by the laws of physics or by some cosmic verdict on our species. It is made by the decisions that civilizations make during exactly the period we are now in. The decisions about how to govern dangerous technologies. The decisions about what coordination mechanisms to build and maintain. The decisions about how to manage the gap between what we can do and what we have collectively agreed to do. These are not abstract policy questions. They are not questions about the long-term future that can be safely deferred to later generations. They are questions about whether there will be a human civilization in 500 years, and the answer to that question will be determined primarily by the decisions made in this century. The Fermi paradox suggests that most civilizations answer these questions badly. It does not say that all of them do. The next time you look up at the night sky, at the silence that should not be there, remember that you are looking at something. Not emptiness, evidence. Evidence about what happens to intelligent life when it reaches the stage we are at now. Evidence assembled over billions of years and millions of star systems and countless biochemical experiments by the universe. We can hear the universe. We have built instruments sensitive enough to detect a signal from thousands of light years away. We have found it empty at every frequency we have checked, in every direction we have looked, across 60 years of systematic searching. The resolution of that paradox is not going to come primarily from pointing better telescopes at the sky, though we should do that too, and those searches may change everything we think we know. It is going to be determined, or not determined, by what we do next. By whether we turn out to be the civilization that understood what the silence was telling us and acted on that understanding, or the civilization that heard the silence and assumed it meant nothing. The universe has been asking this question for 13 billion years in the only language available to it. We are the first ones listening who understand what the question is. Good night.